So welcome, we can start this week. At this lecture, we will start the part which is real differential geometry. We have already something about it, namely what is a manifold. But manifold is just the playground to do something there. And this something is differential geometry, which starts with the concept of a vector in a point of a manifold. And it turns out not that easy, but not complicated. So our aim is to say that if we have a point P, what is something like that? Vector at point P. So we have arbitrary point at our manifold, and now we want to say what is a vector. It is quite simple concept in Euclidean space, as we know. When you started to study physics, you met a lot of vectors and even vector fields. For example, electric fields, magnetic fields, and so on. So it looks that why to make such a big science from a vector? We know pretty well what is a vector, but it turns out that if you go from the Euclidean space to any manifold, it is not that easy. And it must be done from the scratch, that what is a vector, and then to show that the vector which we know in Euclidean space is just a particular case, and Euclidean space is very particular case of a manifold when it is quite easy, but in general it is not so. So in order to define what is a vector, we must do it in a way which is called the sociological way, that vector is an element of a vector space. That first to define some vector space, and then to tell that this vector is an element of this, a guy which is a part of similar guys, yes? So this will be also the case here, that we will describe some particular vector space which is bound to this point of a manifold, yes? And that it is connected with this point in a canonical way. That means not through some arbitrary choices. We will use arbitrary choices for the construction of what is vector, how linear combination is done, but then we will prove that this concept does not depend on this arbitrary choice. That it is standard way in mathematics, that to define something which does not depend on arbitrary choices in terms of using arbitrary choices and then proving that it doesn't depend. Yes? So it will be nicely seen here that this concept works perfectly, or this method. So we will actually define vector in several ways. The concept was known already in 19th century, at least. For example, Riemann and those scientists used it, and especially at the end of the 19th century. So it is not new, but we will introduce much newer concept of vector from the 20th century, and then we will show that from this, as a consequence, is also possible another definition, which will be the definition of the 19th century. Yes, because it is, this 19th century, of course, works, but it is not so intuitive. So we want to have some definition which is intuitive and at the same time it works properly. So the first idea will be the idea of two curves which are tangent in point P. Yes. So the P is this P here. All this happens on some manifold. And then here we have some gamma 1 and gamma 2. They are two curves. And as it is seen from the picture, we want to describe somehow that they are tangent to one another. So consider curves which are here at time 0. So no other curves in this consideration. Then, what is the coordinate presentation of this curve somewhere here? So near the point P. It will be xa of gamma 0, which is P. So xa coordinates of the point P itself, plus d over dt at 0, xa gamma t. We usually call this xat. It is the curve in the Rn space. Maybe you remember that we have the curve here is R1 gamma 2m, and here is some phi to Rn, and this composition is Rn with x's, so it is the composition first gamma then phi, and it is a coordinate presentation of the curve. Here is some p, and here is the curve, and here it is the curve which is described in this way. Here it is abstract curve, and here it is coordinate presentation. So what is it? Make a derivative of this function as a function of t and compute it at 0. Call it ai. It is an element of Rn plus higher orders. So up to the first order of accuracy, in this family of curves which satisfy this, the only data we need to describe this curve is this column of numbers. Yes? Because this is for all curves the same. For all curves which satisfy this. So there is no information in this, also a column, yes, but we just specify to all curves which are here at time 0. So this information is of no importance for us. But now there are curves which go with in several directions, and all that is described by this column of numbers. So, very shortly, xa epsilon is xap with no information value plus epsilon ia. Now, how two curves look like with the same IA? Well, they differ here. Yes, they have some Taylor expansion which differs after the first term. And what does it mean? That they go later on, they go differently. For example, like that. So if some curve gives you some AI column, another curve with the same AI looks like that. At the very beginning, it looks identical with this first curve, and then it has some other decomposition or Taylor expansion. So now we can say that gamma 1 is first tangent to gamma 2, or we directly say that equivalent, because we can check that this tangency is an equivalence relation. you know that there are some 3 points which equivalence relation should satisfy, that if gamma 1 is equivalent to gamma 2 and gamma 2 to gamma 3, then gamma 1 is also equivalent to gamma 3 and so on. And we can check that if gamma 1 is tangent to gamma 2 and gamma 2 is tangent to gamma 3, then also gamma 1 is tangent to gamma 3. So, and what it mean a tangent? That AI of the first is the same like AI of the second one. So if you compute this first derivative at 0, something like velocity, yes, but velocity in coordinates, then if they have the same velocity, they are tangent by definition. And it is meaningful, I mean visually, because it means that at the very beginning they go in the same way, with the same velocity in the same direction, so to speak. So they can differ in higher order terms, and one can also introduce the tangency of higher order, which will be not done here. It is important if you study something which is called jets. Jet theory goes further and introduce, it can stop somewhere and tell you that all this information is jet then at this point, but we will not study jets here at all at this course, but only curves, which are special jets, and curves stop here, yes, after the first order, because of good reason. It is more very interesting case. So now, if we have first curve, first of all, we use some coordinates x's. Which is our arbitrary choice. There are a lot of x's. In this arbitrary choice, gamma 1 gives you A1 from Rn. Some gamma 2 gives you A2, and gamma 3 gives you A3 in general. But if those two curves has the same columns, and also those two curves have the same columns, that of course the first curve has the same column like the third curve. So we see that it is really an equivalence relation. But now what is important is whether this equivalence is dependent on coordinates or not dependent on coordinates. Because if it is dependent on coordinates, it's not very, very interesting. But it turns out that it is not dependent on coordinates. So what is the translation language to translation from one language of x coordinates to some x prime coordinates? We can introduce prime coordinates, as we know. There are some formulas, x primed as functions of original x's. Now imagine that we want to compute this column in primed coordinates. So we express the x prime version of this curve and compute AI primed in the same way, d over dt at 0 of xi primed, and I directly write that to express this is in xi primed means that you compose the mappings just. So you have x presentation of the curve, then you have this formula, x primed as function of x's. So x primed version presentation of the curve is of this way. It is composition at the beginning. So we need to make a derivative with respect to this t. How it is done? First, xi primed with respect to x's, xj, at point P, at t equals 0, and then dxj over dt at 0, which is aj, no, non-primed. Yes? This is Jacobi matrix computed at P. So it is a constant matrix, constant invertible matrix. So the formula, the language is that AI primed is Ji, J, A, J. So very simple. And remember that this is a constant matrix, yes, this J, because it is evaluated at P. So whenever we want to compare primed and non-primed versions of something, we can use this formula. That it is visually A primed is matrix J constant invertible and A. Yes, it is this formula. So now the check whether the concept of tangency depends on coordinates or not. In first coordinate, we have A1I equal, or without indices, A1 equals A2. This means the column assigned to the first curve equals the column assigned to the second curve. Yes? But it is with respect to x. So the question is that with respect to x primed, whether it holds the same, that the two columns, the primed columns, are the same. So what is, by this vocabulary, A1 primed? It is J applied on an A1. Yes, it is written here. Or A is J, A primed JA. So A2 primed is the same J applied to A2. So this J has nothing to do with the curves. It is just the correlation between the primed and unprimed coordinates. Yes? So the same J is here. That because it is invertible, you can say that from A1, A2, the primed version is clearly true. It is elementary. So now it is quite interesting that we can introduce something done in terms of coordinates, but independent of the choice of coordinates. Namely, we can introduce the concept of the tangency, that two curves are tangent at some point. Whenever you have, the tangency is equivalence, and because of that, you have equivalence classes, standardly denoted like that. Standardly, I mean in mathematics, that whenever you have equivalence class is denoted by these square brackets. And we can introduce the set of equivalence classes called TPM. And we call that element of this set is a vector at point P. So what is a vector in this definition? It is an equivalence class of curves starting at P, at 0. One of them. But usually when I say that something is a vector, because of this sociology, I have to tell how it is linearly combined. Otherwise, the word vector makes no sense very much, or it is already coined somewhere in mathematics, so you cannot introduce something which and call it vector, which cannot be linearly combined. So how to linearly combine this object? we again use coordinates. So we have a vector which comes from some curve. This is a vector, yes, by our definition, that it is equivalence class of curves. So here is some equivalence class of curves, and at when we have language X that we use coordinates axis, we have some A from Rn characterizing this equivalence class. The equivalence class is characterized by this column, but only with respect to some arbitrary choice of coordinates. Yes? The same vector is characterized by I primed with respect to x primed. Now, we want to have a linear combination of these vectors. Some sigma W, it corresponds to B from Rn with respect to axis, and B primed from Rn with respect to primed axis. And we want to define gamma plus lambda sigma, because we want to make a linear space out of this set TPM. So how to do it? Here, recall that these columns are from Rn, and Rn is a natural linear space that we can make linear combinations of two columns. In this way, as you know, that it is one of the first example of linear space, that columns of numbers. So, recall that we have some set which has no linear structure, but there is a bijection to a set which has linear structure. So, what we can do, we can steal it simply. Because there is a bijection, if you want to make linear combination of these abstract vectors, just find their friends in the very concrete vectors, which we can linearly combine, do the linear combination with these columns, and then go back. From the bijection, you can steal the linear structure. Officially, it is called induce, not steal, yes? So we can induce linear structure to this set TPM from Rn, because there is a linear structure in Rn, but there is a little problem there, that this bijection is non-canonical. It depends on the choice of coordinates. From here to the same vector, you associate a column with respect to axis, but another column with respect to primed axis. So the bijection between your set and useful set Rn is not canonical. That's why it is a little bit problem. But it turns out that if you defined the linear combination in a standard way, in terms of any coordinates, the result will become the same. This is non-trivial fact. So what we do, simply if we have those two vectors, we say that the result is A plus lambda B with respect to axis, and n primed plus lambda B primed with respect to primed axis. This is the definition. That how to linearly combine these abstract guys, associate with the first one the column A, with the second one the column B, and then make this linear combination, as is well known, and then go back, because there is a bijection. Yes, but now the question is that if we do it in this picture and this picture, will it be objectively the same linear combination? So the question is, if I do my linear combination in the first language and then translate the result already to the second language, whether I get the same thing like if I do the linear combination directly in the second language. If this is true, then it means that this linear combination is well defined, in spite of the fact that it is done in one particular language. Now, how these primed are done? Here is the technical answer. Just multiply by j. So primed here means that whether it is true that it is this. Yes, and it is clear that it is true. It is a simple matrix fact. That because of this way how to make linear combination of columns, it is clear that this is true, yes? So the answer is yes. It is technically completely trivial, but the content is rather untrivial, that you can introduce linear combinations of such abstract objects like the equivalence classes of curves in terms of any coordinates, and then if you do it with respect to other coordinates, you obtain objectively the same thing. So now, because we already have linear structure, check it if you do not see that it is consistent. So we have the linear structure here. Not just a set, it is a linear space. And what about its dimension? There is a bijection to Rn, so the dimension is n. And it is a linear mapping now already, that this bijection defines linear structure here, so this bijection becomes a linear mapping. So, what we learned, that at any point P of a manifold, you have an n-dimensional vector space, which is called tangent space at point P of the manifold M. So it is our discovery, today's first discovery. By the way, what about the basis? We already know that there is a space n-dimensional. What about the basis? Because of this bijection and linear isomorphism now, we can introduce the basis again by stealing the basis from Rn. In Rn, you have something which is called natural basis, that 1, 0, 0, 0, 1, 0, and so on. So this will be called E1, E2, and so on. And we can say that there is a basis in our TPM which we obtain by the isomorphic mapping of this basis put here. Yes. Now, because our scientific vectors in TPM are equivalence classes of curves, so we are interested what is the equivalence class now? Some J which corresponds to Ej. Ej now is from Rn, and this is in TPM. Elements of TPM are equivalence classes of curves. So what is the curve itself, for example, or the class, which corresponds to the basis which we know of this form? Yes? So we have to go back that xi t is xi p plus epsilon ai, this formula. And now we put as an element ai here, the basis element. So imagine that here is, for example, the first one. That this is, for example, 1, 0, 0, 0. So what does it mean? That the curve goes like that. All components or coordinates of the curve do not change to first order, but the first coordinate changes a little bit, linearly. Yes. So x, y, epsilon is x, y, p plus epsilon. Yes, epsilon times this 1. And x2 epsilon is just x2p plus nothing. And xn epsilon is xnp plus nothing. There can be something with higher orders, yes? But up to first order, we have the basis E1 corresponds to such curve. If we define that there is nothing here more, then we call such curves coordinate curves. So-called coordinate, this is the coordinate expression of the first coordinate curve. First coordinate curve is such one that all coordinates are constants, except for the first one, which linearly grows with t in general. So, for example, now on these coordinate curves. We have a sphere with coordinates theta and phi. Already in coordinates, I make a picture. Here we are somewhere, and now the first coordinate curve is this one. And the second one is similar, but the change is here. So here, the theta coordinate grows linearly and phi coordinates is constant. So how it looks like on this picture? Can you describe me that how I should make the picture for this curve? If this is theta 0, phi 0, yes? This point is P, theta 0, phi 0. Then what about this curve? How it looks like? If this is Earth, here is North Pole, South Pole. So how it goes, this curve, expressed like that in coordinates? Do you remember how theta phi are defined? Phi goes in this way, and theta goes from the North Pole down. So this curve looks like, in which direction it goes from theta 0, phi 0? Yes, in the direction of south. There is some meridian, I think, and it goes in this way. Here it is at 0, and then it goes to the South Pole, along the meridian. And what about the second curve, coordinate curve? It goes in which direction? East, exactly. It goes like that. So at each manifold, at each point, or the vicinity of the point, you can define these curves. And now, what about the equivalence classes, for example? this corresponds to equivalence classes of all curves for which this is an representative. So all curves tangent to this one is in the same equivalence class. So what they look like, this one, but also something like that. That first they go along the first one, and then they can go as they wish. So all these curves are in the same equivalence class, which corresponds to the basis vector AI 10. This, and here A1, A2 is 0, 1. And the equivalence class is this curve, which goes along the meridian to the South Pole, but also other curves which go in different ways later on. In the epsilon vicinity, they are the same to first order, and then they are different, or can be different. So, this is the whole story of vectors in this language. You see that, well, this language is intuitive, it has this advantage, but the working with bases like that is not very practical. So, we now go to another definition, which will be equivalent, and which has the advantage that from this another definition, we obtain some practical means how to compute with vectors, actually. We introduce something which is called start with vector in the first picture, yes, as we done yet. So let's have this vector in the language of axes. We assign to it something which is called directional derivative of what letter? A function, because I will use it, some f. And I will write here that it is fm. I will speak more about this. These are smooth functions on manifold M. All smooth functions on manifold M are denoted like that, fm, f functions. So we have a smooth function, and now we apply something denoted by hatted v. Here is v as a vector. Yes. By definition, it will be d over dt at 0, function f at gamma t. And we claim that there is a mapping v goes to v hat. This is from TPM, vector on the manifold in the first language. And this will be from something which I will denote temporarily as hatted TPM, but at the very end we will have just one TPM. I say that in a moment we will have the third definition and the fourth definition, but already more or less trivial in comparison with the first and the second. First and the second look different, and the third and fourth are a little bit trivial when we know these first two. So actually we will have four definitions of vector, and we can introduce TPM for all of them, but because they will be equivalent, there will be just one TPM. But first, let this be TPM and here some hatted TPM. So what are elements here? Directional derivatives, like that. Because we understand that if we have a manifold, here is our gamma, here is P, gamma at 0 is there. So what is gamma F computed at gamma T? That it is, here we have F, and we compute that the directional derivative, it is derivative when we go in this direction, how F changes. Yes, it is given by this formula. But notice that there is one small tricky point, that here is full gamma, and here V is just equivalence class of gammas. So there are many gammas in this equivalence class, and here is one particular representative. So it is a little bit suspicious. Yes, but we will see that, well, there is no need to be suspicious because it works. So actually this derivative doesn't need more from this gamma than this information which is just in the equivalence class, the beginning. It is more or less clear because this derivative doesn't use long gamma. It is not sensitive of how gamma is here, yes? Because the derivative is computed at the very beginning, at P, at t equal 0. So that's why the directional derivative only takes information about the beginning of the gamma. And the beginning of the gamma is fully described by this column A. So let's compute it in coordinates. In coordinates, we have coordinate presentation of this F. We have coordinate presentation of curve. So this altogether is Fxt. So d over dt at 0 is of this is derivative of f with respect to xi at t equals 0 and dxi over dt at 0. But now this is exactly this column ai. So we see that in coordinates it can be written like ai, which are numbers, and these symbols applied on f. You see that by definition, this is that make a partial derivative of this f, and at the end compute it at t equals 0, that means at the point P. So this symbol makes two operations. First, make partial derivative, and at the end, evaluate it at point P. And it is multiplied and linearly combined, so to speak, with these coefficients ai, yes? So what we see that, first of all, we indeed do not need more information from the curve, like the information hidden in this column. That means information if this, of this presence to equivalence class. Not the whole f, not the whole gamma, but just equivalence class of gamma is needed. So for both vectors and these guys, these directional derivatives, the same information is needed from the curve. Just this column needed here and here, this column ai. So now we see that there is a useful mapping that whenever we have a vector, we know that it means that in coordinates xi we have a column. we can assign with this vector a directional derivative, which is something completely different. What is this directional derivative? It is a mapping from Fm to R, because the result of this directional derivative is a number. Now, how it behaves, this directional derivative? First of all, this Fm is not just a set, but it is the algebra of smooth functions. And what algebra associative? What does it mean? That you can linearly combine functions and you can multiply them. What is the definition? This at point x or p is fp plus lambda gp, and this at point p, again by definition, if is fp gp. This is pointwise multiplication. Then you use the fact that the function goes to R, and in R you can do this associative multiplication. This is multiplication of real numbers here. And here also the linear combination of real numbers. So because our F has this as a target space, and this target space is algebra, then the functions on M is also, the functions of M to R also give you an algebra. Now, this mapping goes from algebra of smooth functions to R, so it should be nice to study how it behaves on the algebra structure of this algebra, Fm, that what happens if you act on linear combination, and what happens if you act of the product. Yes, this some mapping from algebra to somewhere, so it should be interesting to study what about the algebra structure of this mapping. Because it is just this kind of derivatives, we see it clearly because we know how derivatives behave, and we check that it is this behavior. And here it is a little bit tricky. And the tricky point is this thing. If it were not be G evaluated at P, we can call it Leibniz rule. Yes? But it is not completely Leibniz, because Leibniz rule means that act on the first guy and let alone the second one, just as it is. But here you do not let it as it is, because as it is a function, and now it is a number. And the number comes from evaluating this function at point P. So we can make some name for it, say Leibniz rule associated with point P or something like that, some unofficial name. But just I warn that it is not completely Leibniz. Yes? Such mappings are called sometimes functionals. There are many functionals, and this is one of them. And because of this property, that how it behaves on linear combination, it is called linear functional. But check that this is also a linear functional, that evaluated if you evaluate function at point P, it is also a linear function. It is also a mapping from Fm to R, which is linear. So here you have combination of two linear functionals actually in this formula. One of them is because this is linear functional from here, but here is also another linear functional, just evaluation at a point. Very simple linear functional. So combination of two linear functionals in the way of Leibniz somehow, yes? And now there is a simple exercise, I will put it to offer for exercises that check that if you have some V1 and V2 which have these two properties, then you can define V1 plus lambda V2, linear combination of them. And they are also linear functionals defined like V1f plus lambda V2f. This is the definition of this object, including the second property. It is quite important. But check that such linear functionals have the structure, natural structure of linear space. Yes, we have a linear space of linear functionals. Linear functionals are elements of the space, and this is the rule how linear combination is done within this set. So, if this is true, and you can check that this is true, just a small check, but useful, of course, then we see that this mapping, that we have a vector in the first way. Now we associate a linear functional to this vector, but these linear functionals of this type, which we study, also comprise a linear space. So we have a mapping from one linear space to other linear space, and this mapping is linear. It can be checked, or maybe it was already done. And the most important thing that it is a linear isomorphism, canonical linear isomorphism. The way back is a little bit not completely trivial. That if you have, imagine that you have formally defined some V by these two properties. What we want to prove in this backward way, in this way it is simple, but the backward way is rather tricky, that you should to prove that there is no way to realize these objects like to create a directional derivatives. The directional derivatives is the only way how to create these functionals. Yes? There is some lemma for it that if you have a given this functional, linear functional, with also this property, then you can somehow prove that the same functional acts by just directional derivative, nothing more. I do not have the strict proof in my book, but you can find it in some books on internet. The proof. It is more or less clear, but you know, in mathematics, and this I can recommend you that try to find some proof somewhere. It is not in my book, but it is not very hard. It is not very hard, but I do not think it is so important that you should read it. I just recommend that if you have time enough, then have a look on this proof. After either believing or checking this proof, we know that TPM is canonical isomorphic to TPM number 2. So from now on, we can say that vectors are either equivalence classes of tangent curves or linear functionals which map from Fm to R, and linear is here, and have this property also. Because this property, without this property, you have more linear functionals, much more. For example, this one evaluated at P. But check that evaluating at P doesn't satisfy this. So it is different. But if you want linear functionals which also satisfy this point number 2, the only way how to do it is to construct some directional derivative. And it turns out that directional derivatives are very practical objects. We can introduce useful bases and so on. Where is the basis? You see that we have a formula in coordinates, this one. So what is V itself? V itself is here. So what is the basis? The basis is here. Because our linear space is a set of appropriate linear functionals, also bases should be linear functionals. Yes? Now, is this guy a linear functional? Well, act on f plus lambda g. So, what should we do? First, we should make a partial derivative of f plus lambda g, and at the end we should compute the result at point P. Yes, and we know from course of analysis, hopefully, that it is a linear operator. Yes, and how it behaves on the product, we know from the course of linear of mathematical analysis that it behaves like that. Yes, because it is standard derivative. We know how we work with standard derivatives. Now, because we have this isomorphism, where is it? It was here. TPM isomorphic to the second TPM. And here we have basis with respect to some coordinates, this one. And here we had a basis, you remember, gamma I in bracket. It turns out that they correspond one to another. That in this isomorphism, this vector corresponds to this vector. It is very easy, I can put it to exercise. Now the third definition, already now trivial. Or no, first, computation in different coordinates. How we compute this in different coordinates? We know from the course of analysis that it is like this formula. It is chain rule, the chain rule. Now, if we put here P, we put also here P and also here P. So it is just G, J, I at P J, yes. So we see that we have a simple way how to make transformation in this language from the language of x coordinates to the language of prime coordinates. Now, what is then the transformation of components? What are components? These are called components of the vector with respect to this basis. So if we have the formula that in the language of x's, we have this, and it should be in other language it is the same vector. Now the vector in the they are from this TPM. Yes, the linear functionals are now vectors. This is the basis, and this is components. In the first language, in the first version of what is vector, in TPM, we have gamma was AI, gamma I, the class. This was a vector, these were basic vectors, and these were components. Yes? Here, this is the vector, here is basis, here are components. Now, how these components transform? Now we just computed this, so instead of this P and this P, and here at P, we have a I, G, I, J, J primed at P should equal the right-hand side. So this should be this, because here is prime basis and prime basis. So we see that we have the formula J primed is Ji, I, or A primed is Ja. And do you remember that we have this formula also in the language of tangent curves? So we now derived that if our way of defining vectors is in terms of linear functionals, then this is basis corresponding to this basis in the language of tangent curves. So also the components are corresponding, that if we had sometimes this vector with this not very practical basis, now we have much more practical basis, partial derivatives evaluated at some point. This is the basis of linear functionals. This is a general vector written in terms of coordinate axis. Here is general vector in terms of coordinates axis primed, primed axis. And because we can recalculate what is the relation of the primed and unprimed partial derivatives, we know it from the course of mathematical analysis, we can now compute what is the relation of components. And the result was this one. And it is consistent with our first definition. Yes, this is good. So it doesn't matter whether you work within the first definition or the second definition, because the results like that are the same. But this is much more practical. To compute partial derivatives is much more practical thing, like to compute some equivalence classes of coordinate curves. It is not very practical way to compute things. This will be extremely practical. We will see that it is extremely easy. Maybe now it is a little bit, messy in the beginning, but when we finish this formalism, you will see that the practical way of computing with this is extremely simple. After this computation, now we can introduce the formally third definition. What is a vector? Vector is this guy by definition. So what? Vector is a linear differential operator with constant coefficients combined with evaluation of the result at point P. That's very, very long story in words, but very short story in a formula. This is a vector, this operator. Remember that in the second definition, this was abstract, that vector is some linear functional which behaves in this and this way on functions. Here it is completely openly said that vector is these differential operators when you use coordinates axis. And of course, if you change coordinates, it is the same story with primed coordinates. Yes? And the fourth definition is even more simple, that what defines you this operator? This is one, in coordinates always the same. So one operator from another operator, you can distinguish by these guys, these numbers. So these numbers are enough. So what is a vector? A set of numbers with respect to coordinates axis with a property at point P. Yes, it is at point P. Vector at point P, it is the definition of 19th century, is a set of real numbers and pieces which are connected with coordinates which you use. But if you change coordinates to primed coordinates, you will have other set of numbers, other column, and the correspondent of these columns is here. Yes? So if you study differential geometry in 19th century, this will be definition. Here you have, by the way, they didn't introduce manifold. Manifold is a newer concept. So you have coordinates xi somewhere here in some coordinate patch. Within these coordinates, you want to define what is a vector here. You say that vector here is some a1, an, somehow connected with this point. And how we see that it is connected with this point, that the second part of the definition says that if you change another coordinates, if you choose another coordinates, then you should have another column of numbers, and the relation of this column and this column is given by this relation, but this j is to be computed here. Yes? So this is inside this j is a point where you compute this j, and this is the information about this point. That's why this column is connected to this point. That it changes to another set of another column in the way which depends on the point, because the Jacobi matrix you should evaluate in various points. Yes? So actually it is bound to this point by this formula. So this is completely equivalent to our definition, but these modern definitions in terms of tangent curves and in terms of linear functionals on functions are nicer to work with and more intuitive, especially this tangency definition. Yes, it is completely intuitive. Here, if you have some columns transforming in some strange way, well, you can see that and why it is that. And I don't know what was answered in 19th century, but for us, I think that it's much better to understand the first definition, the second definition, and then to see that this definition is completely compatible. So we can use it, but in a way we understand it. Week 6 was the tangent space. The tangent space is this. And by the way, now I will just read this notation for any version of these vectors. Yes, first, second, third, fourth, still they are objects from this vector space. By the way, how they are linear combined, clearly, yes, that if you have a column and another column, do it as it is usual with columns. So linear structure is also here. It is trivial that how such two linear operators will be linearly combined. Linearly combine these columns, simply. So the tangent space we know. Vectors various equivalent definitions, and this is called, the coordinate basis of this vector space. And maybe I explained it that this is called the tangent space. Space at P. Now we can perhaps go to vector fields. So, what can be a vector field? Simply a vector at each point. Yes. Symbolically, I will put this arrow, that vector at P is this guy, just for thinking about some situations. This is a good idea to draw pictures and to think in pictures. So here is some Q, another, let's W. Imagine that you have all points of your manifold, and in all points you have vectors in either of these four possibilities. So we will say that we have a vector field on manifold M, but we need to define what is a smooth vector field. Yes, because here these vectors are completely unrelated in the definition as it is. But they cannot be non-smooth because we want anything in differential geometry at least in this course, introductory course, everything should be smooth because unsmooth things are more complicated and we do not want to go to more complications that needed. So, in order to define simply what is a smooth vector field, we can think like that let this V be a vector field in this intuitive way. Then we can act with this vector field at a function and obtain another function. This will be a mapping f goes to Vf from Fm. How it works? If I claim that this is some function of Fm, I need to say that what is value at P, some number. Yes, each function has some value at any point P. And definition will be that it is V at P applied on F. Yes, V at P is a functional. So it produces you a number from function. Think it over, that is a very nice definition. Then we already know that we have a function, but still we can have non-smooth functions. I wrote that it is a smooth function, but now another definition that V is smooth if Vf is smooth for all f. That this is a mapping functions to functions. And now, smooth V means that acting on all smooth functions, you will get smooth functions and nothing more. Whenever this is smooth, this is also smooth, by definition. This is definition of the smoothness of this V. What is smooth function? We already know, yes? But now we want to know what is smooth vector field. So we restrict on smooth vector fields, and now how they can be described in a practical language. At any point P, we have that V at point P is this functional. And this functional can be written in this way. We know it already. Yes. Now, at point P, it is a linear functional that we know. Vector field comes that at point P we know what is a vector, but now we define that at each point you have such object. Now, how can we write this V without P, at any P? So, it should be like that in any point. So what should we do? First of all, we should put away this P, right like that, because then when we go back to P, I will add this P. Now, this symbol means for any P, it is computing of partial derivative. And this is a constant at P, but it may be other constant and other P in Q. So here you have some AI, here you have some BI, and so on. So in each point, this directional derivative is given by some column. So if we make this column depending on point, you will have a vector field. What does it mean? That you will have AI as function of x, that it depends on which point you compute this column. And usually it is not written as A if here is V. So what is usually done, that to write it like that. Yes. So there are two steps. First of all, put away this evaluation at P, because it is automatical. If you want this vector field to evaluate at P, then put it here P, and also give coordinates of P, and you will have some real number column. But you have now a column from functions. They wait to be evaluated at some point. That's why they are functions. So you see that it is even simpler to write vector field in this language than to write the vector itself. Yes, because you have know this evaluated in P, because it is automatic that it is a set of linear functionals at each point, and each of them is of this structure, so the set of linear functionals can be written like that, without any p's, because it is for each p. The p is given by the value of x's. Now, how it behaves, what kind of mapping it is. In mathematics, maybe I didn't tell you that I read somewhere it was quite nice that anything which makes sense in mathematics can be expressed like map, some sentence. Whether it is true or not, I think that, well, it is more or less true. So, vector field was defined somehow. Now, can we define this vector field as a map? Answer is yes. It is a map from Fm to Fm. I recall that the vector in a point was a functional. This was a difference. Vector at a point is a linear functional, so a mapping from Fm to R. But vector field can be described as a mapping from Fm to Fm, and what it does, that take some function and make this. And what is this? Here it was somewhere written what is Vf at point P. So put P away. This is at any P. Yes? Once again, it is even simpler than that. But you should understand this definition first, and then to understand that this is quite nice to write it in this way. How it works practically, here is our way how to express V. So it is in coordinates. This is abstract way. Remember, this is abstract way, no coordinates needed. But if you have coordinates, you can do it like that. So you understand that if you have a function, then make partial derivatives of this function, then multiply it by some functions, vi, and then put it all together, summation, you still obtain a smooth function. Partial derivatives do not change smoothness. And now we see from this that we defined smoothness of V in terms of smoothness of this mapping, that if this is smooth, this complete function should be smooth. Now, if this function is that guy, we know from mathematical analysis that partial derivatives do not spoil smoothness. And now, if you multiply smooth functions by some functions, what we need from these sum functions in order that the result will be smooth again? If you multiply smooth function with non-smooth function, is the result smooth function? Not always, yes? Or maybe never. So you need these guys to be smooth in order that this guy together is smooth. So if you want to have a smooth vector field, if you write it in coordinates, you need smooth components. These are called components of the vector field. Components. And they are components with respect to either that or with respect to coordinates x. Because this basis is uniquely given whenever you start with coordinates. Components with respect to this basis. So, a vector field can be treated as a mapping from the algebra of functions to the algebra of functions. Again, just apply this. Notice that it is a linear differential operator. Now, in coordinates, vector fields is a linear differential operator with non-constant coefficients. This is the difference with vector. Vector is also linear differential operator in coordinates, but with constant components. And vector field can have non-constant components. But still it is a linear differential operator. And because of this dependence on x, well, or not only because that, it can be treated as this mapping from functions to functions in this way. Now, this is an algebra. How it behaves on the algebra structure, this mapping. Because we know how partial derivatives behave, we can check that first of all it is linear. And now at product it behaves in this way. Which is a real Leibniz now. So G is not evaluated at P, like here. Yes, here was G evaluated at P, so this is something like Leibniz, and this is Leibniz. So what is it? It is not a linear functional, because here is no R, but it is a linear operator. It is linear operator in the vector space Fm, But because Fm is not only a vector space, but it is an algebra, there is also a product, it behaves nicely at the product, and nicely means according to Leibniz rule. Yes, so it is a linear operator which behaves according to Leibniz rule at the product in this algebra. It is more than a linear operator. And do I have some time? Yes. We can now compute the useful thing that if this is the coordinate expression of a vector field, what about going to other coordinates? Something like here. The same V is Vix partial derivatives with respect to I plus, not plus, but at the same time Vi primed, x primed, prime derivatives. Now this can be written as prime derivatives times Jacobi matrix at x. So it is not a constant Jacobi matrix. All this is at any x, at any point on the manifold. So we see that this should be, if we write Jj, should be this. Vj primed x primed is Ji x Pi x. This is the way how components of a vector field transform to other coordinates. Example, I will not compute, but example. We have a vector field in R2 using xy coordinates in standard plane. Vector field V minus y derivative of x plus x derivative with respect to y. Yes, it is of, where is the formula? Once again, Vix derivative with respect to I. So in the plane, when you have coordinates x and y, this will go to just two possibilities, derivative with respect to x and derivative with respect to y. It is 1 and 2. So here should be some function, in general, Vx x y derivative with respect to x plus Vy x y this. This is concrete realization in a two-dimensional plane of this expression. So here is still more concrete. This is the most general vector field, and we just somehow used that Vx as a function of xy, let it be this guy, and Vy, let it be this guy. Why not? They are smooth functions. Yes, they are smooth functions. Now we can recompute to R phi, this vector field. Polar coordinates. Formulas: R cosine phi, Y R sine phi. You can check that after computation you will get just this simple vector field. So what is it? In general, in polar coordinates, we have R phi derivative with respect to R plus V phi R phi derivative with respect to phi. This is the most general vector field in polar coordinates. Now, computation shows that this specific vector field in Cartesian coordinates, after recomputing to polar coordinates, has very simple components, namely nothing here, 0, and here just 1. which are, once again, smooth functions. Yes? Smooth vector field in one coordinate transforms to smooth vector fields in other coordinates, and the result is check that this simple expression. So that's all for today. Thank you.